Yeah, thanks everybody for coming. My name is Christian. I'm a postdoc here. Thank you, Emma and Christian, for organizing this course. Yeah, so I will be giving 6 lectures about the Hill-Hopkins-Ravenel solution to the Kervaire invariant 1 problem. And my first lecture is a bit of a introduction to some of the basic tools that go into that through a sort of easier example, which is the Hopf invariant. And yeah, so I'll start out by just introducing the Kervaire problem first so that we know what we're all headed toward and then get into that. Maybe I just want to first ask who here loves filtered spectra. So maybe raise your hand if you love filtered spectra. So one thing I'm going to do is use the language of filtered spectra quite a lot. And if you're anything like me, you splurge for the hardcover edition of this, and you read it every day before you go to sleep. So if you're one of the people that didn't raise your hand, then I can recommend that as a sort of conversion. Yeah, but I guess more seriously, since it is a mini course instead of a course, that does entitle me to kind of assume some things. And I would say in general, I'm not going to try and be too heavy-handed with stuff, but I will, for example, also talk about stacks without really giving a whole introduction to that. Mostly because I would like to tell the story in the most kind of conceptual way, even if that's not the most sort of elementary. So anyway, but if you have questions, please feel free to ask. Okay, so I'll get started. So first, let me introduce the main goal of the course, which is to give a proof of the Kervaire invariant problem. And so I want to briefly describe the geometric background to this problem. So starting with the work of Kervaire-Milner, they defined the following set. We looked at the set of smooth N manifolds homotopy equivalent to the n-sphere modulo the relation of H cobordism. Okay, and the kind of main first thing that they observe about this is that this is an abelian group under connected sum. And this gave them an invariant to be able to understand exotic spheres. Yeah, thank you. Okay, so for example, once you know this and you know some of the big theorems in differential topology, questions about exotic spheres turn directly into questions about this group theta n. Okay, so for example, if I look at the H cobordism theorem as proved by Smale, plus the proof of the Poincare conjecture, Perelman. These two things imply that if I take my n to be not 4, then the n-sphere admits a unique smooth structure if and only if this group theta n is 0. So in dimension 4, I guess basically none of the tools work, but everywhere else this question is completely reduced to understanding this group theta n. Okay, so Kervaire Milner also proved a bunch of results about this group. Which allow us to start to understand this. So going to let k be greater than or equal to 0. And I'm going to let jk be the J-homomorphism in degree k from pi k of the infinite special orthogonal group to the stable, the kth stable stem. Okay, and in short, they basically show that this theta k group is controlled by information about the stable stems, basically in the co-kernel of the J-homomorphism. Okay, so they prove the following facts. So in dimensions 4k, theta k is just the co-kernel of J. They show there is an exact sequence as follows in odd dimensions. So there's always a map from theta to the co-kernel of J. And in these dimensions, they identify its kernel. And its kernel is just the subgroup consisting of those manifolds that bound a parallelizable manifold. So the BP is like bounding parallelizable. Okay, and then we have the following exact sequence. So in 4k plus 2, this map is injective. And it continues to an exact sequence as follows. Yeah, so I guess it's a de-looping of that. Or rather a looping of that. So this is just like you take a matrix and regard it as an endomorphism of Rn, and then 1 point compactify it. That gives you an endomorphism of Sn. And this gives you a map to the loop space. You take homotopy groups. Yeah. Yeah.
In your definition of BP, should we swap n until n?
Sorry?
In the definition of BP, are you looking at those spheres bounded parallelizable manifold?
Yes. Bounded parallelizable. Ah, yes, sorry. Let me just write that. M bounds parallelizable manifold. Yeah, sorry, thank you. It is, yeah, it's exactly the opposite of what I wrote. Okay, and this exact sequence we are just going to take as the definition of the Kervaire invariant this phi k. Okay, it has a different definition geometrically, but let's just take it to be the one coming from this exact sequence for now. And finally, they show that is not 0. Okay, so this is kind of all we need to say quite a lot about the existence of exotic spheres. And I just want to introduce Browder's theorem. So again, so we know a bit where we're heading with all of this. He shows that this Kervaire invariant theta k is non-zero if and only if the dimension 4k plus 2 is of the form a power of 2 minus 2, and a certain class in that degree survives the Adams spectral sequence. So I won't define that class right now, I will later. But the point is, this theorem relates the non-triviality of this this phi k homomorphism to something in the Adams spectral sequence. And okay, that is the theorem that Hill, Hopkins, Ravenel prove. So they show the following. So they show that this Kervaire invariant is non-zero if and only if the dimension is one of these values of 4k plus 2. Okay, so let me be clear about where the attributions should go. So Hill, Hopkins, Ravenel show that the only possible dimensions in which this is non-zero is these ones. Some earlier work, some of it of geometric origin, some of it of more homotopy theoretic origin, using this theorem above, showed that it was non-trivial in all of these dimensions, and then these three authors finished the classification by showing it's also non-trivial in this dimension, again using the Adams spectral sequence interpretation. Okay, so let's put these facts together. This completely solves the question of exotic odd-dimensional spheres. So this tells us the only odd spheres with a unique smooth structure are S1, S3, S5, and S61. Okay. And then it also tells us a lot about even spheres, although it doesn't give a complete classification. So if I take n to be not equal to 2, then the 2n sphere has a unique smooth structure, if and only if n is 1, 3, 6, 28, or n is greater than 70 and the co-kernel of J2n is 0. Okay, so I claim that this corollary follows from this theorem and the theorem of Kervaire-Milnor, which is not so hard to check. And yeah, maybe the point is, of course, it's great that the odd sphere case is completely finished by these theorems. And also, the even sphere case is quite interesting because it says if you want to find an even exotic sphere, you just have to take a big dimension and then find some class in the stable stems which is not in the image of J. And we have a nice conceptual way of thinking about the image of J. It's the height 1 part of the homotopy groups of the sphere. So if you can find any class in the homotopy groups of the sphere that's of height greater than 1, then you have an exotic sphere. And so lots of people have worked on that. At height 2 in particular, where we have quite a lot of access to height 2 classes in the sphere coming from TMF. So there are also a lot of dimensions more that we know there to be even exotic spheres in using height 2 information. Okay, that's all I'm going to say about the Kervaire invariant for today. Are there any questions so far? Yeah.
Are you sure about in point 3, the exact sequence, are you sure about the last map to 0? If the map from Z2 to BQ4K plus 1 is also surjective?
I'm pretty sure I copied it down, so it's a matter of whether I copied it down right or not. But pretty sure that's it, yeah. And I think that you need to know that if these corollaries are to follow. So, yeah. Okay. Okay, so now I want to get into the Hopf invariant 1 problem. Okay. Maybe just set this down for a minute. Okay, so right. Okay, so yeah, this Hopf invariant 1 problem I hope is a bit of an introduction to the way that the Kervaire invariant problem is solved by the Adams spectral sequence. But I want to just focus on this for today. So the Hopf invariant 1 problem can phrase in a few different ways, but let's just say it this way. When does the n sphere admit an H-space structure? So that is, when does it have a homotopy unidal multiplication? That's the Hopf invariant 1 problem in one form. And the answer, which is due to Adams, is exactly those spheres. Okay. And, well, you can see right away that these are H spaces because they're the units in the unit. Yeah.
With H space, we just remove the multiplication and V versus associative, and this S7 is something that.
So S7 is not associative.
It's not associative.
Right. Yeah.
I'm just wondering what the word H space is.
I thought so, but let's say homotopy unidal multiplication. Yeah, so in these cases, these are the unit vectors in these four real division algebras, which is where they get this multiplication from. And the kind of basis of the proof of this is to translate this into a question in the Adams spectral sequence as well. And this comes from a geometric construction which constructs some particular complex out of the H-space structure. And just to motivate that, instead of explaining the construction, I'm just going to say that if you do that to these ones, you get the sort of second projective spaces in each of those cases. Okay, so let me just state a proposition then. So the proposition is that if Sn were an H space, then we would have a space Xn, I'll call it, such that the mod 2 cohomology ring of Xn had the following form, where Xn is a class in degree n. Okay, and the point about knowing this ring structure is that because Xn is in dimension n, this gives a non-trivial square n on Xn. Okay, so that's the sort of first step. Let me erase. Sorry. Oh yeah, it should take.
You mean just name all space, or the n follows that product of X?
Oh, sorry, that's just a notation. X superscript n. Where's my? Yeah. pretty dry. Okay, so the first thing I want to do is make the situation somehow slightly more comfortable by working with spectra and by working with homology instead of cohomology. So the first thing I want to do is just assume for now that Sn has an H-space structure so that we can construct this space Xn. And then I get out of this a spectrum I'm going to call Yn, which I get by taking the suspension spectrum of Xn and desuspending it n times. And I want to look at the homology of this. And I know already that it has two classes, one in dimension 0 and one in dimension n. Okay, and I want to trade the, let me do this. I want to trade the steam rod action on Yn for a coaction of its dual. So right now we know something about this map. And I want to just take the dual of this map and call that psi. So we're using that homology and cohomology are dual. And this is the steam rod algebra A, and this A star is the dual of the steam rod algebra. Okay, and this was an action by an algebra. This is a coaction by a coalgebra. And it's just going to be more convenient for us to write it this way. Okay, and the sort of main point there is that we know a great description due to Milnor of this dual steam rod algebra. So it's a Hopf algebra, and it's given as an algebra by this polynomial ring, graded polynomial ring with the generators in those degrees. And the coproduct, which is what is most important for this coaction of a coalgebra, is then defined by the following formula on the generators. With the convention that C0 is equal to 1. Okay, and well, what follows immediately from this square n that we had over here is that I have the following description of this psi coaction map. Okay, and that's because that's because of the following claim. So Milnor identified the dual of the steam rod algebra as this polynomial Hopf algebra. This thing has a canonical basis given by the monomial basis. So you can pull it back to a dual basis of the steam rod algebra. That's called the Milnor basis. And in that procedure, the monomial C1 to the n has as dual basis vector square n. So that means that when I just take this description of this action map and apply the dual to it, I'm going to get this formula. Okay. Any questions on that? Okay. Great. So the kind of point of view on this that will lead us into the Adams spectral sequence is the following. So I can look at the following cofiber sequence. So I take the inclusion of the bottom cell into Yn, and then I take the cofiber of that. And this lifts the following algebraic diagram. So this is This is, well, a short exact sequence of comodules over the dual C-node algebra. So it's an extension like this of comodules. And this line here is what's remembering for us that we have this C1 to the n coaction. In particular, it's a non-trivial extension because this coaction here is non-zero. Okay, and so I'm just going to now use this to define my bigraded X as follows. Okay, and so the point is we have some topological lift of this algebraic extension. So, of course, the first thing we can do is just work purely algebraically and actually try and compute this X1 group and see if that obstructs the N. Okay, so how do we compute X1? Well, we can compute it via the Kervaire complex. So there's a canonical resolution of the trivial comodule F2 as a comodule over A star via this Kervaire complex. And so this gives you some kind of canonical way of computing these X groups. And let me just take that as given for a moment and write out what it is. So I have this big chain complex. This map is the map sending a class X to X tensor 1 minus, well, in general, I'm taking a comodule and I have a coaction map psi. In this case, my comodule is the trivial one F2, so this psi map ends up just being the unit of this Hopf algebra. But in general, the Kervaire complex would look like this. And the second map looks like that. Sorry, let me separate this. Okay, so the second map is this alternating sum. I have a class X going to X tensor 1. I have the coproduct for the Hopf algebra. And then I have, sorry, that should be 1 tensor X. Okay. Great. So in particular, one thing we see right away is a really explicit description of X1. So this is in order of cohomological degree. This is the cohomology of the complex here is X0, cohomology here is X1, and so on. So this X1 star is in particular the set of classes in the dual C-node algebra whose coproduct satisfies this formula, which is the definition of saying that the class X is a coalgebra primitive. Okay, and anyway, that gives us a relationship between extensions and something fairly concrete. And if you look at this formula here for the coaction, it's not so hard to see that this is not very big. So let me just write it this way. This turns out to be, well, X1 n, say A star. This is equal to C1, 2 to the n, 2 to the k, 1n is the power of 2, and 0 otherwise. So this is just coming from evaluating this coproduct formula and observing that you don't get this formula on so many monomials. Okay, in particular, we already know purely algebraically that n has to be a power of 2. Okay, but we also know that purely algebraically there's nothing more to be said because these X1 classes are non-zero. So we have to somehow get a better idea of the distance between the topological extension and the algebraic one. And that's where the Adams spectral sequence comes in. Okay. Great. So as a kind of sloppy way of motivating the atom spectral sequence, let me say as a kind of philosophy on many spectral sequences that appear in higher algebra, you have some functor, some derived functor like x, f, and you know how to apply it to the homotopy groups of something, and you would like to define some higher algebra version of that, tf for topological f, in such a way that you have a spectral sequence of this form. So somehow you can go from the information of the derived functor applied to the homotopy groups to the information of the homotopy groups of the higher algebra version of the functor. And moreover, as a part of this philosophy, you should be able to cook up this picture with the Whitehead filtration. Okay, so I'm not proposing a general way to define TF, just that if you have a good definition, you ought to have this spectral sequence. And well, let's figure out how to define our TF when f is x. And I propose to do it by looking at the way we computed it via the Kohlbar complex. Okay, so this gives us, well, the following definition. Let me define the following cosimplicial object. So using that F2 is you need F2 to be an E1 ring to define this. F2 is an E infinity ring for us. We have this cosimplicial diagram in spectra, and it's just built out of the unit map for the algebra F2 and its multiplication map. So here, this map A to L is using the unit on the left. This is using the unit on the right, and this, sorry, that's not delta. Call it mu for multiplication. Okay. And I want to sort of propose that that, or perhaps its totalization, should be, you know, the kind of TF in this context. Okay, but really I'm after this spectral sequence. So that's the way I'm going to define the Adams spectral sequence of the sphere, at least. Is I want to take the following composite. So I have this cosimplicial spectrum, and I want to compose it with the Whitehead functor to filter spectra, and take the totalization of that composite. So this Whitehead functor, this is the functor associating the Whitehead tower to a spectrum. If you don't know what the Whitehead tower is, probably you know what the Postnikov tower is, and this is the same information. It's the tower built out of the connective covers of a spectrum. Okay, and of course the sort of purpose of it is that its associated graded gives the homotopy groups of the spectrum. So let me state the following proposition. So the spectral sequence associated to Adams S has signature E2 is the derived functor f that we had, converging to the homotopy groups of the sphere, completed at 2. So yeah, I mean there's an FP for any prime version, but we're just going to look at F2 today. And moreover, this spectrum y2 to the n exists if and only if the class Hn in X1 survives the Adams spectral sequence. Okay, so I guess there's two claims. One is about the signature, and the other is about that this sort of idea actually worked. namely that this spectral sequence did give me some kind of obstruction theory going between the algebraic extension data and the topological one. Okay, and I'm just going to prove the first claim. So, some space. Okay. Are there any questions about anything? Or is this? I would say the signature terminology is something before that, before higher algebra, just namely, yeah. It just, if you have a spectral sequence, you know where it starts and what it ends at. Yeah, that's, I guess, what I mean by signature. Yeah, I think myself and others may have been caught using that word in higher algebra ways before, but here not. Okay, yeah, just, yeah. E2 page and the abutment. Okay, so, well, the proof is as follows. The E2 page of a spectral sequence associated to a filtered spectrum is just the homotopy groups of the associated graded of the filtered spectrum. Okay, and that's really why we wanted to use the Whitehead filtration, because we know it's associated graded. So first of all, taking associated graded is like a co-fiber construction in a stable category, so it commutes with limits. So I can pass it inside the totalization. And the tensor square, thank you. And then I can try to understand the limit inside. And the point is that that is just taking homotopy groups. Okay, and this just spits out the cosimplicial object associated to the cosimplicial object to which the Kobar complex corresponds, as I discussed earlier. And then you just have to believe some fact that says if I, look at this diagram of cosimplicial abelian groups, say, and I regard it as a cosimplicial object in the derived category that's level-wise discrete, that taking this homotopy limit is exactly under the Dold-Kahn correspondence computing the cohomology of the associated chain complex. And that's true, and that finishes the argument. Okay, so I didn't prove the statement about the abutment, which is harder to prove, but I just wanted to show you why using the Whitehead filtration is a nice idea to make these kinds of spectral sequences. Okay, great. So now we have the Adams spectral sequence, which gives us an obstruction theory to the existence of this y2 to the n extension in terms of the algebraic extension. And Adams proved that that n can only be less than or equal to 3 by showing the following. If I take n to be greater than or equal to 4, there is a differential in the Adams spectral sequence as follows. Okay. And he proves this using, well, I mean, the proof is basically something to do with secondary Steenrod operations. And it is, in some sense, from a certain point of view, a purely algebraic proof. But conceptually, it's sort of not, because it's using these higher operations. And so my goal in the second half of today is to give a different proof of this theorem of Adams that doesn't proceed directly via the Adams spectral sequence, but uses the Adams-Novikov spectral sequence instead. And this is a sort of baby case of what appears in the Kervaire invariant 1 problem. So let me just give myself a little breathing room for the second half and introduce that. Okay, so the Adams-Novikov spectral sequence, as you would expect from the name, is something very analogous to the Adams spectral sequence. And it's defined exactly in the same way by replacing F2 with mu, the complex cobordism spectrum. So using really any E1 ring, I can form this cobar complex here. And then I can form this filtered spectrum in exactly the same way. And so if I do that with mu, that's the definition of the Adams-Novikov filtration. And well, using the same argument, you can identify the E2 page of this in terms of certain X groups. This turns out to be X in the category of comodules over a Hopf algebroid, which is slightly different than the situation with F2, where it's just a Hopf algebra. But it's really all the same kind of thing. And the sort of main tool that allows us to trade this problem in the Adams spectral sequence for one in the Adams-Novikov spectral sequence is that, well, first of all, these converge to the same thing. So this converges to the homotopy groups of the sphere. And also that there's a map between them. So, just by definition, this cobar construction is natural in maps of rings. And so this filtration, Adams filtration construction also is natural in that. So if I take the truncation map of mu, which is connective, and it has pi 0 equal to z, and then I take the map from z to f2, that gives me a ring map from mu to f2, which then results in a ring map in filtered spectra between these filtrations. Okay, and maybe I'll just finish by stating something which I want to state as an exercise, because it's just easy but also kind of instructive, which is the following. Use this map of filtrations to prove that if Hn survives the Adams spectral sequence, it emits a lift along the map on E2 pages. Okay, so this is the group we calculated before. This is where Hn lives. And the claim is that, yeah, if this survives, then it actually emits a lift on the E2 page. So that's not really immediate, from the fact that they converge to the same thing. It comes from the fact that this class here has such low filtration, and from the fact that these X groups vanish in filtration 0 in this stem. Okay, I'll say more about that later. But I think, yeah, so the exercise is super easy, but maybe what I mean by it is to write it down in terms of the filtration, so in terms of the bigraded homotopy of the filter spectrum, and use tau, and yeah, I think it's a nice way to see how how the tau formalism works for a map of spectral sequences. Okay, let's take our 15-minute break.